So prior to that, so here our entire discussion, the magnetism, what I started here. So let's go back to solenoid. Can you remember solenoid? So go back solenoid. So this will be to explain all this. I'll take help of solenoid. Let I be the current. Then it will produce a B bar. That B bar will be in this direction. B naught. And let N be the number of turns on it. So what is the expression for magnetic field? B equal to mu naught Ni. What is N? What is N? Number of turns per unit length. Let L be the length. Let N be the number of turns. So this B naught, okay, no? No, as I vary current I, the B naught will vary, definitely. The B naught vary. So first I'll define. So what is that B naught I should call? So magnetic field intensity or a magnetizing field. Any name shall we give for it? Yes, the B naught hotband is called as a magnetizing field. The first definition I'm bringing. We don't have very good suitable information on this, the definitions what I'm putting. Just carefully understand, nothing, no much thing, just only to understand. And the solenoid always keep in mind. To study this magnetic material, you are going to take help of solenoid. In the books without solenoid, they explain. That's why you find very difficult. They are just focusing on quantum nature. Since we don't know quantum mechanics, we just take an example what we know it. We know solenoid. Yes. So by varying current, I can produce this magnetizing field. I'll call magnetizing field. So now, what is this space here? This is the free space. Even I take this solenoid, I'll go to the space. Free space means no medium. That one. Will this field, can it exist? Yes, if there's a current I flows, the field will exist. So what is this magnetizing field here? It's a field which can exist in a free space also. This is one basic parameter. And it will induce magnetism in other substance. So what is the magnetizing field? The symbol for this is what? B naught. It's a field that can exist in free space and magnetize the other substance when placed in this field. It can induce magnetize here, or you can put it like it can induce magnetize, or you can magnetize that one. Magnetize other substance when placed in magnetize other substance. So what is the meaning of this? Or it will induce magnetism, or it's a field that induces magnetism in other substance. There's the external field, you can call that one. Okay, after this, magnetizing. So there's a magnetic, what do you mean by this one? Magnetic induction. You go back to electrostatics. Go back to electrostatics. So there's a capacitor plates. Just correlate things, little bit easy for you. What is this? There's a E naught, no? Now I'll bring a dielectric slab. Let me bring a dielectric slab. There's a dielectric. So there are two fields are there, no? The E naught will be as it is. And this E naught, what it will do? It will induce magnetic field. It will induce charge. So because of that, EI will come. So what is that E naught? Whether you keep slab or if whether slab is there or not, that E naught will exist, no? Look at the first diagram. If you remove slab, E naught will vanish, nothing to do. And what is EI? Induced electric field. Similarly, what will happen? So when I bring any magnetic substance, if I bring any magnetic substance, and I'll pass a current I. This current I flowing here will produce magnetic field in this direction, B naught. Okay, fine. And it will induce magnetic field. So it can induce magnetic field in any direction. So let me put it BI like this. And what is this rod? It's a magnetic substance. So what is that BI? BI is called as induced magnetic field. Will induced magnetic field. So the symbol will be BI, or if you want to write it as, yeah, okay, some. Let me take this one only. In the books, they brought BM, induced magnetic field, B naught, that one. So I'll carry on the book convention. BM, what is BM? Induced magnetic field, that one. So who will induce that magnetic field? This magnetizing field. So I'll come to later on. How to measure that induced magnetic field is what? Who will induce that magnetic field? This current, no? Now, by varying current, tell me what will happen. See, B naught is some sort of entity. Can I control how much B naught can I control? How to control how much of B naught? By varying N or I. So I do have control on B naught also. So for to express that, the control on magnetic field B naught, no, I'll bring another quantity, magnetic field intensity. Or there's a magnetizing field intensity or magnetic intensity. Magnetizing, or this is also called as magnetizing field intensity. The symbol is H. What is H? H is equal to N into I. How to define this? How to define this one? The ability of magnetizing field to magnetize a material medium. Or nothing but it's a measure of how much that magnetizing field which can exist in space and which can magnetize other substance. How much magnetizing field that we are expressing by H. I think it's quite clear. So what is now B naught you can write. What is the relationship? B naught equal to mu naught into H, that one. The relations between B naught and H. And if you look at all the higher electrodynamics books, they don't go for B naught. The H is what matters here. All the applications what we discuss H only, not B naught. These are the two terms related to magnetizing field only. Okay, let's come for the substance will get magnetized, no? How to express that magnetization? Means like, let's come for this one. How much the field is induced? Now, if I put wood, there won't be induced electric field. There won't be induced charge. So then this will also get electric dipole moment. We'll agree this. So inside that, the you can say atom will get polarized and will get induced charge. And because of that, this particular slab will have net dipole moment. So now how much it got induced. So all that particular thing and what is EI. So that everything is what happened. Now I'll go into the material. Okay, now I got what is the electric field E naught. On that one, and what it does and how to control E naught by varying Q naught. and by varying area of cross section. The similarly, how to control B naught? By varying number of turns per unit length and current. Okay, let's get into magnetizing field. This magnetizing field, how much a substance got magnetized, I should measure, no? I should have a quantity to express that how much a substance got magnetized. So for that purpose, how that Bm is related. So Bm is given by, I think I'll go for next page. Or let's write here only. The next one is intensity of magnetization. This is called as capital I. Small I for current, capital I we use for this particular quantity. So it is like a defined as magnetic moment developed per unit volume of a material when placed in a magnetizing field. Is called as intensity of magnetization. This is. So then what is the dipole moment? Now what is this particular material made up of? Total magnetic moment. This intensity of magnetization, magnetic moment per unit volume. What is this magnetic moment should be equal to? From where this magnetic moment I should measure. So what is the magnetic moment? The individual atom, what happen will behave like a magnet. Then the number of atoms into dipole momentum of each magnet will become the magnetic moment here. So this particular thing, N into okay, let me keep time being here. So magnetic moment, so what we can write as like a Qm into 12, like it's similar to bar magnet, you can go for it. And volume will be A into 12. So this will become magnet. What is this? I introduced some terms like this. Can you remember this pole strength? M naught, again you'll get confused. So there's a pole strength. I'm bringing that one. North pole. And there's a north pole. South pole. Let length be 12. And the side length, let it be A, that one. So what is the question that is being asked? So per unit volume, no? Thickness is also, yeah, fine. So what is a dipole moment? So can we define dipole moment like this? Pole strength into magnetic length. Then into, this is the area of cross section. No? This one. So now area of cross section into that length. What it will be? It will become volume. So that 2L get cancelled. So the pole strength per unit cross section is what we can define intensity of magnetization. Now, what is that induced magnetic field? I'll bring into the picture. The induced magnetic field BM. Can you remember? I think BM, induced magnetic field. Now I can relate with this one. So because now the substance got magnetized, so we can write it as mu naught into intensity of magnetization. The induced magnetic field, I'll do express like this. So what is induced magnetic field is equal to Bm equal mu naught into Im. So some books they given symbol capital I, you may get confused with the current. Intensity of magnetization. I think in SC or my easy, you follow this symbol. Let me carry on with this one. So the induced magnetic field, how to measure that one? Mu naught times of particular the intensity of magnet. How to calculate intensity of magnet? Total dipole moment of the dipole moment of the substance per unit volume. So what is the dipole moment? We just put like a bar magnet. Let's say that in the iron rod, it gets magnetized. Then I'll measure the pole strength into magnetic length, will give the dipole moment, total dipole moment of bar magnet per unit volume. So it's nothing but pole strength per unit area. We can also define this as pole strength per unit area. Like this, what happened? We're able to express that induced magnetic field. Now, in a substance, what is the total magnetic field now? The total magnetic field now, we can define it as, okay, I'll bring this diagram. What is the resultant magnetic field? The total magnetic field, the net magnetic field, B is equal to B naught plus Bm. What is B naught? B naught is given by mu naught H. What is induced magnetic field? Is given by mu naught into I. What is this Bm? Induced magnetic field. B naught is magnetism, and this is B is a net magnetic field. So this will become mu naught H plus I. Okay, this, what you should call this one? Net field, net magnetic field in a material. This one. So what is this? This is a material. So I go back to see. Don't get confused here. What is the net field? We write E naught minus E I, no? So then why don't you write B naught plus Bm? If Bm opposite to B naught, I'll write B naught minus Bm. If Bm is induced magnetic field in the direction of external field, I'll write B naught plus Bm. So it can be plus or minus. It all depends on material. I just picked up a material where the induced magnetic field will be in the direction of external field. Okay, agree this? Let's not bother ourselves much here. It can be plus or minus, no doubt. Okay, now after this, so I got now something different. So next I'll go for magnetic permeability. Fifth one. What is the magnetic permeability? The name itself, it says permeability, permits how much material will permit to get magnetized. It's a measure of the ability of substance to get magnetized. Is it okay? The ability of substance, it's a measure of the ability of substance to get magnetized here. So, or permits how much of magnetism it will permit inside that material. How much of magnetism the material will permit. There is nothing but called as a magnetic permeability. So the definition says like it is the measure of the extent. Different books, they're given different way of explanation. You can follow very generalized one. I'm just putting in a very simplified way. I think even if you take SC Orma, he directly went there. Some for 2 or 3 parameters he defined, he went it. So even in NCERT book, we don't have any description much here. It is the measure of the extent to which a material can be penetrated or permeated by a magnetic field, by a external or magnetizing field, will write by a magnetizing field here. So this is defined as mu, symbol is mu, which is equal to B by H, that one. Or B is equal to mu into H, this is. Next, similarly, relative permeability. Relative permeability. So where is that magnetic permeability? Can you go back to the electrostatics? Absolute like a permittivity of a medium. Then we had absolute permittivity. Then we have relative permittivity. Similarly, what happened? We'll get here relative permeability. What is another thing? It is a measure of the extent to which a material can be penetrated or permitted by magnetic field, or it's a measure of, or it's a measure of ability of a substance to get magnetized. BM can be right or left. I'm telling this one, BM can be left or right. It all depends on material. There are only two possibilities, BM opposite to B naught or BM in the direction of B naught. Finish, or no much further discussion. BM is not due to relative permeability, mu r. First, what is the permeability? Permeability is like it's a ability, or I'll put one more simplified. It's a measure of ability of a substance to get magnetized. Means, say, very first question. The substance which I'm going to put in a solenoid, will it get magnetized or not? I should know, no? Will it get magnetized, or how much it will get magnetized? All that, what happen, everything what happen will determine the permeability. And what is relative permeability? I can compare, say, iron, it will get more magnetized. Next, copper, it will get less magnetized. Able to get this one? To compare the magnetization of different materials, I need one more quantity that I'm bringing mu r. To it is measure of degree of magnetization between various material. Compared to iron, what about copper? So then whom I should take reference? It's a measure of degree of magnetization between various metals. Who is a reference? The free space is a reference. So for that purpose, the mu what happen is written as mu naught into mu r. I think you got exact picture now. Compare the iron is having mu r, say like some 6 lakhs, 6 lakhs 24,000. If you take some aluminum, no, it is having only around some 20. So substitute mu r for iron, how much? 6,000, 6 lakh 24,000. For what happen aluminum, let it be 20. Mu naught is some sort of fixed standard. Now, which is having more permeability? Yes, no, the iron. So what is this one? Relative permeability. It will help us to compare the degree of magnetization between various materials. Now let's come back. I told you there are some materials where the induced magnetic field will be opposite to B naught. There are some materials where the induced magnetic field will be in the direction of B naught. So to indicate that sign of Bm also, we need one quantity. For that purpose, I'll bring the last one called as susceptibility. It is called as the symbol chi. This is. Now, so what to write here? Again, it's a measure of the ability of substance to take up the magnetization. Nothing but same thing. It's similar to that one only, but it will tell us the very clearly in what direction the BM is, like, you know. So it's a measure of It's a measure of nature of magnetization in a material. So this susceptibility, I'll define it as intensity of magnetization by magnetizing field intensity. So in books, they're given dietary definition. It's defined as ratio of intensity of magnetization to magnetizing field intensity. Of course, you can memorize definition, but what is the meaning of that? It's a measure of nature of magnetization. Nature means Bm in the direction of B naught or Bm in the direction of B naught. So that is what reflected by chi. I think now we are in a better position. No? So first, I think I'll just summarize one so that it'll be easy for you to the coming concept. What is this? There's a field produced by solenoid and it can exist in free space, no? Magnetizing field, which will induce magnetism in other substance. Then how much this magnetizing field, how much magnetizing field intensity, you see, B naught is a field, how much B naught is what H. I think it's a quite very simplified way is what things are being put. Intensity, intense means how much, how intense magnetizing field. Finish sure. Magnetic field intensity they call, but you do remember this one, magnetizing field intensity. B naught is magnetizing field. How much magnetizing field is what H. Induced magnetic field Bm, because in the material some magnetism will be induced, that is Bm. Next again, how much the substance got magnetized. So what is this? Magnet developed per unit volume of material when placed in magnetic field. In other ways, what you can define intensity of magnetization, how much, it's a measure of how much a substance got magnetized when placed in a material, when placed in a magnetic medium. I'll write it here. So intensity of magnetization, one more definition. It's a measure of I think it's quite clear now how much the substance got magnetized. That measure is nothing but the intensity of and how do we measure magnetic dipole moment per unit volume? Leave it. Come for this one. Then next again, it's a different materials. How much they get magnetized? They can get magnetized. I should know that one. That is what mu. Then again, to compare the magnetization of different materials, furthermore, I'm going, that is mu r. Then next, susceptibility. The induced magnetic field can be in the direction of B naught or opposite to B naught. To express that, I'm bringing susceptibility, nature of magnetization. So like this, all these things are related. Okay, let's get into the basic thing. We have started like this, no? B is equal to B naught plus Bi, induced magnetic field, or Bm. B naught is what? Mu naught H. And what is Bm? Bm is mu naught I. H plus I. Then what is I is equal to chi into H, susceptibility into H. So further this, H you take outside, 1 plus chi. What is this? There's a net field, no? This net field is due to what? Because of material medium. So this will become mu H is equal to mu naught H, 1 plus chi. What is mu? Mu naught mu R. H will get eliminated. So what is mu R? 1 plus chi. This relation between the relative permeability and the susceptibility. I think there's a very fundamental thing. This is what you have to remember. Nothing big. Okay, no, I think now we have enough of definition. So we'll get into the the material. The first one is what? I'll introduce the classification of magnetic materials. Now, good numericals they can ask you just based on these definitions also. Just only that formulas, if you remember, it's okay. Now, first is the diamagnetism. What is a diamagnetism? Means again, there are three materials are there. I will take a rod